Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today, we will discuss about color fundamentals and processing. So, here our objective is to consider processing of color images, and in the previous topic we discussed how color images are represented into three components, into red, green, blue. Today we will understand the reason behind that representation, and to understand that how color is actually we perceive color in the nature. Now, one thing we should understand that color is not a very innate property of an object, rather it's a kind of our experience, our visual experience. So, it's a psychological property of our visual experiences as a result of the presence of an objects and lights, and when you look at it. So, this is our experience. While looking at the objects, we experience color. So, it's not any physical property of those objects or lights. As I mentioned, it's an interaction between the light in the environment and our visual system. Now, when we consider the physics behind this kind of color sensation, so one of the very early characterization of color sensation is what we have already known from school physics, that this is nothing but a sensation produced by the optical light into our visual system. And optical lights, they are kind of electromagnetic radiations, and there are particular wavelength range which has this it has certain wavelength range, and each wavelength is attributed to a particular color sensation. So, in a very simple way, then we can say color is an expression of or a rather sensation of the stimulation of an electromagnetic radiation on our retina or in our visual systems, and which depends upon this wavelength. So, we have shown the spectrum of this spectrum showing the color for different wavelengths here itself. As you can notice that this is a wavelength, say 400 nanometer, and this is 700 nanometer, and the kind of variation from violet to red, that kind of different shades of colors are attributed to this wavelength. But this is a kind of little bit of physical property, I should say, behind the color sensation. But this is only one factor. But there is the other things, that how actually this sensation is processed in our brain or in our visual system through the sensation through our eyes, and then it is carried out through a nerve system through our optical nerves, and then it is processed in the brain. But one of the very early part of this sensation is that there are certain receptors in our system which is sensitive to this particular spectral spectral band of the electromagnetic radiation, which is the optical band. So, it is not the same, the response is not the same for every electromagnetic wave. So, we call it a kind of visual sensation or visual relative sensitivity of our visual system for different spectral bands. So, here we can find that it is more sensitive towards green zone, and whereas for the blue and the red zone, it is less sensitive. We will understand it further. So, it is just the luminance sensitivity functions which shows that we are more sensitive to the green lights. So, one of the consideration that how when we are sensing color is that what is the kind of light source that is illuminating the scene. That is one factor of our color experience. So there are actually three factors as we can understand. One is that light is falling on an object surface and then it gets reflected, and then the reflected ray is passing through our eyes and it falls on our retina, and then that sensation is carried through optical nerves to our brain and we experience color. So the first component, what I described in this pathway, that the light source, the basic cause of color sensation. So how light source is characterized for this color experience? As we have I just mentioned that a light source again contains several electromagnetic waves of different wavelengths. So the amount of energy for each wavelengths in that optical band and their relative distribution, that can characterize a light source. So we can say that it is energy emitted per unit time, which is basically power at each wavelength, and this relative spectral power can just characterize a light source. So one such example has been shown, just any arbitrary variations. So it could be the energy distributions or spectral power distributions of a light source. There are some very simple way of characterizing a light source and with temperatures, because some of the known spectral profiles we call, say, relative spectral power distribution, say let us call it as a spectral profile of a light source. So there are certain kind of radiators which is acting like a light source, which radiates electromagnetic waves due to its temperature, and black body radiators are is a kind of radiator which is ideally which does not absorb anything. It simply it's a radiator with near zero albedo. So it is basically, it absorbs. It's a black body. It absorbs, rather it does not reflect. It does not reflect any amount of energy. It simply absorbs whatever energy is incident, and as a result, from it has certain temperature, and then it acts as a radiator, and it emits the electromagnetic radiations from that hot body. So one of the way you can construct a black body radiator approximately, that you can consider some hollow metal object, say spherical object, and make a very tiny hole, and the radiations coming out of that hole, maybe it basically mimics the black body radiator. The interesting part of characterization of black body radiator, it has been observed that they follow certain spectral power distributions, which means the spectral power or energy emitted per unit time, depending upon the wavelengths, it has certain specific relationships. So this is the relationships. This is the famous Max Planck's spectral power distributions, and in this equation you can see the constant, like Planck's constant is there, and then you have also the velocity of light, and then this T is the temperature, which is expressed in Kelvin. Lambda is the wavelength. So this is how it is related, and this profile has a certain kind of profile is there. So something like in physics book you may find that there is certain kind of profile for this kind of energy distributions, which has certain peak in between some wavelength band. Now everything depends upon temperature, because all other constants are there. So with the varying temperature of the black body, you will get different profiles. So when we have certain spectral profile of a light source, and when it is similar to one such distributions, then we can equate that light source with a black body. You can say it's it's a black body source with certain temperature. So simply we can associate with a temperature. So many a time different kinds of light sources, they are simply associated, they are described in terms of this Kelvin, the temperature scale itself. So this is the characterization of one factor for producing color sensation. The next second factor, as I mentioned, that the incident ray gets reflected from the surface point of an object, and those rays, reflected light is passing through our eye and falling on the retina, and it produces, it receives energy, and there are receptors which carries those sensations in the retina. So we are talking about this second part of reflection phenomena of an object. So here there are certain object properties which actually takes part in this interaction process, and that is how we consider some of the color properties we associate with these object points. So this property is the amount of reflections, reflected energy that object surface is providing to our sensation, which means there is a property called coefficient of reflection, so which gives you the fraction of energy that is being reflected from that point, and it depends upon the surface. And also coefficient of reflection is a function of wavelengths. So like as I mentioned that a light source have a spectral profile, similarly every surface point or every surface in a sense they have certain spectral profile, reflectance profile, we call it reflectance profile over the varying wavelength. One example could be you consider this banana, and if the surface of the banana or skin of the banana which is a yellowish color, and if I consider its reflectance profile, that means its coefficients of reflection is much larger, much significant in this range, and where in this range it hardly reflects any amount of energy. So this is this actually modulates the amount of energy that we receive through our retina. So finally we can say that the color signal or the signal what is received by our optical system or through our eyes, we receive this energy in our retina. It is this energy could be considered as an interaction of this incident or stimulation from the light source and the reflections on the surfaces. So interactions between light and surfaces. So there are two factors. One is say illumination, it has its spectral profile. Then there is reflectance, it has its spectral profile. So naturally you can consider reflectance will simply multiply with the factor of illuminations for a particular wavelength. So at every wavelength you get a modulated energy distribution, spectral power distribution. So it's a pointwise multiplications for each wavelength, and then you get again another spectral profile of the received color signal which our sensors are receiving in the retina. So this is the genesis of the color signal, and our visual experience is dependent on the type of signal that we are receiving. So we can say that this experience or this observed color is the result of interaction of light source spectrum with surface reflectance. But there are third factor now will be coming into this part, that this signal is processed in our visual system, which means it is received by the cells in retina, and then it is converted into kind of electrical pulses through this nervous pathway, and through the optical pathway, and through the different kinds of in that pathway also there are processing, there are different kinds of cells are there, and finally it goes to our brain for processing. So we will rather here concentrate on this receptor part. Rest of the part would be like processing of a signal through our system, which we are not going to discuss here. Our color experience is much more dependent on these characteristics of this receptor also. So let us try to understand that what are the properties of those receptors and how this signal is received at our visual system through eyes. So in that case, we may consider an analogy of our eye. It's like a camera, and as you have a lens in a camera, Similarly, we have a lens in the eye, and any light when it comes through the environment, it passes through this lens and it falls in a particular surface on our retina, on our on the eye, which is called retina. So it's not exactly the planar shape; it has a spherical surface, as you can see, and the receptors are there that is being received. So we have a lens, and like a camera, as we can adjust the focal length in camera by some means, by moving the lens here and there, but we have certain muscles which can do, and which is much more stronger, much more flexible to adjust those focal lengths. Not only that, a camera has an aperture, so which gives you the field of view. So we have also an aperture. So we have lens, then the pupil. Pupil is there. It's a dilation of pupil will increase the aperture. So that is one, and then controlling the both focus and focal length of the camera of this lens and also this aperture. We have iris, and those are the muscles which controls this. Anyway, so through this window, through this opening, the energy propagates, energy comes into our falls into our retina, and in retina there are different kinds of cells. So there are photoreceptor cells, and particularly two categories of cells are there in the retina. One category is called rods because of the shape is cylindrical. The another category of cells is called cones, which is the shape is conical. And like a digital camera, as if these receptor cells are also acting like an array of sensors, or in any optical camera, conventional optical camera, earlier we used to have more, where there is a film where it's like a film where it receives optical energy, and then that in the film it's a chemical reaction that takes care after that. Anyway, so as I mentioned, it is more I should say convenient to understand in terms of array of sensors, because these rods and cones are discrete cells and they act like a sensor. So rods are mostly for low illumination vision and cones are for high illumination and color vision. And not only that, even for cones also there are three types of cones. Now we just name them as red, green, blue because they are spectral, they have spectral sensitivity. Say rods do not have much spectral sensitivity. It is broadly act over all wavelengths equally. It's a low illumination, but it works on low illumination. If it is brighter illumination, rods are mostly saturated. It does not have much effect on that. But cones, they work on high illumination, and also it is meant for color vision because of this. Because in the cones we have spectral sensitive cells, and there are three types of cells. One are more sensitive to the red zone of the optical spectrum. That means they are of higher wavelengths. The other one, so we call them red cones. The other type of cone is sensitive to the middle zone of that spectrum. So we call it, so which means it is morely the green band that we have seen earlier. And the third type is blue cone, and which is sensitive to the smaller wavelengths zone. And also in the physiologically, we have observed that the ratio of these cones are also not even. That means you have 10:5:1 ratios, which means we have more red cones than green cones, twice the number of green cones, and more green cones than blue cones. So almost 5 times. So this is the kind of ratio we have in our cell. And in our retina also, there is a very small area which is almost near in the middle, but just beside the optical nerves. There is a small area which we call fovea, because most of the focusing takes place at that point, at that small area, and it just assumes 1 or 2 degrees. So if I assume the optical center, so if I consider a cone from here, the fovea, it will be about 1 to 2 degrees. So this angle should be 1 to 2 degrees. So it's a very narrow angle and very small area. But the density of cells or these cones is much higher. So you don't get much rod, you don't get any rod cell there. It will get on the cones there most, and very high density. Hardly you will get blue cone also. Mostly red and green cone. Rods are mostly rods mostly occur in the periphery, and they are responsible for peripheral vision also. So as I mentioned that cones are mostly concentrated in fovea. So I talked about these three factors, and when we consider color perception, now we can abstract out the color signal part and concentrate more on the functioning of these receptors, because then we can understand that how color is really, why color is represented by three components, as we discussed in the just we mentioned in our first topic itself when we discussed about fundamentals of image processing. So for that, okay, so we will be now discussing this color perception, as I have said, that suppose this is the spectral power distribution of the received signal which falls into our retina, and in our retina we have three types of cones, which means each one with this sensation, with this kind of stimulation, will produce certain responses, and those responses depend upon the amount of energy you have within the wavelengths where it is more sensitive. So it's like a linear system. You have done linear system where you have the spectral in the spectral domain. You simply multiply the spectral responses with the power, and you can, if you can aggregate, you can or integrate, you can get those responses. So these are the three types of responses. So finally, color sensation can be encoded into three aggregated responses of these receptors. So that's why it could be represented by three numbers, and so the one direct inference from this is that you can have different kinds of spectral power distribution, but it may happen that because of this filtering of three receptors, you are getting exactly the same numbers. So which means different light sources may produce a similar sensation of our color, and we call them those kind of light sources, we call them metamers. Some example is shown here. Some of the example color signal, I should say. It's not light source only, it is color signal spectral component. So the signal received for example, for white petal and signal received by white flower, you can see the spectral power distributions are quite distinct, but still we look them as white. So they are examples of metamers, right? And this is also another interesting theoretical way of justifying how metamers could occur. So here you can see that if you have a spectral power distributions of your color signal like this, and another one is this one, and if I consider all those visual responses of these three numbers, say you have respective red zone, then say green zone, and then say blue zone, or so their aggregated responses may be equivalent. You can get just an average one. So they can also, they are the possible candidates of metamers. So far we understood now color experiences could be represented, or in a way the color could be represented as a three vector form, which means the three component form in the vector form. So it's in a vector space you can represent this color. Now the question is that if I give you these three components, suppose as we can know, we have already, as an analogy, we see that we have a red filter, green filter, blue filter in an optical camera, and then we sense the red component part, green component part, blue component part, and that represents for the same color signal, and that represents certain color of that signal. Now can we understand that with these three vectorial representations, what color it is? So that is one of the key questions for color processing. So there are some calibrations, scientific calibrations for producing the color charts, where given these three components, it is related to the physical color of a signal, and there we relate it to the equivalent electromagnetic wavelength of the electromagnetic radiation, which gives you this kind of color sensation. So again, as I mentioned, though color is not a natural object or natural property of any innate property of a natural object, but still the wavelength of electromagnetic radiation acts like a guiding, I should say, provides a guidance of our color experiences. So the sources which has single wavelength, we call them monochrome sources, and they are very important in this case to understand this color experience. So to standardize these experiences, what we can do, suppose you have a monochrome source, which means it produces color signal of single wavelength, and suppose you have some ways to produce color signal of produce a superposition of three monochrome primary color sources. So they give, and can vary the quantity. So which means you have those three components of those primary. Say you have red source, green source, blue source, all are monochrome source, and then you can vary their intensities and you can superimpose them. So that puts a kind of mixing, and those are the three components. So the resultant color what you have, that color, if it is equivalent to the color of the monochrome light, so you can associate the ratio or the proportion of those three components as the attribute to that color of that wavelength. So that is the kind of experiments people have designed, and they did color experiments, matching experiments for that. So I just describe this, and schematically once again let me explain it better. So you can see that there is a monochrome source. It's like greenish monochrome light source, bit dark greenish, and you have say three primary sources, one for red, say one for green, or for blue, or any other primary sources could be there. We'll discuss that how the primary characterization is there. Anyway, so if I vary the quantities and project them on a screen and superimpose them in right proportion, so and note that proportion, then we say, so these proportions of say red, green and blue, they actually they represent the wavelength. So this is a particular say wavelength, say lambda naught. So this is equivalent to the sensation produced by a monochrome light lambda naught. So this is how you go on doing this by varying this wavelength. So you can vary the wavelength here, and so you can just vary it, and you can also perform the same experiment number of times, and you can just make a chart. So that is how you can produce color chart there. But this is not the case is not so simple. So we'll come to another situation. Actually, what happens that there could be see in our visual system, it is not that we sense color only through this additive mixing of primaries. Now there are our filters, particularly the red cone filter. We'll show it later on through the spectral graph. Actually, in some wavelength band, it also produces an inhibitive part. So that means it's a kind of subtraction. So it's a negative response. So it's a mixture of positive and negative values. So these vectors in not necessarily be always positive components. There could be a negative, and that is for only red component in our systems. So there are colors, which equivalent colors which needed to be produced for that sensation, produced by those primaries where even the negative mixing requires, which means subtractive mixing is also required. Now this is difficult because as you see that the experiment what I have designed, it is based on the additive mixing, but there is a way you can get this information. So that's the other situation I am explaining. So you consider a monochrome light of a particular wavelength, say once again some wavelength say lambda naught. Here say it is dark reddish color, for example, and you have three primaries. Now however you do the mixing, you are never going to get this color because of that property, because you require one subtractive part. So what you do with some innovative way, instead of working with all three, you can move one of the filter, say one of the source here, you can add them one of the source here. And then now what you can find that, okay, and so the amount you add here, then you are trying to bring both of them with the same sensation and record that. So this is still this is that same monochrome source, and this is another primary, say P2 primary, and this is P1 and P3. So you are varying P1, P3 and P2, and then you are trying to get two colors in the similar range. So this part, since you are mixing it here itself, as if you are subtracting it from this component. So you show this response as a subtracting response. Now this is a hypothetical case. As I mentioned that mostly the rate component, it becomes negative there. It is the net rate component. But no, in this case, just for the example I just mentioned. So this is another subtractive mixing we have to get, and from there we get the representation, full representation. For any wavelength, we get the corresponding color chart of necessary mixing proportions, which may be also negative in some quantities. So that is that. So finally, to summarize these particular observations, inference, that as we can see that color experience or color representation is guided by this kind of trichromatic decomposition of the color signal into three factors, and that produces the sensation. So the trichromacy is a law by which the color could be represented also. So it's a kind of a property for color representation. Now, as I mentioned that say there are three primaries colors. By mixing them, you can generate the equivalent sensation. Not only additive mixing, theoretically subtractive mixing. Technologically, it is not possible to get both. One of them only. I will come to that part later on. But what is the characteristic of primaries? Now we say those are primaries if they are independent. It's the same linear algebraic I should say characterization of any linear system, algebraic of any linear system. So where the basis vectors, set of vectors are considered, and if I say independent vectors, which means linear combination of other vectors cannot produce the one which is the remaining one. So in that set, then we can say independent. Similarly for primaries also, if you take any two, their linear combination, whether it is additive or subtractive, will not produce the other color. So it must be independent. That is the property of primaries. And there are another law of nature is that the encoding of color into this or experiences in factorized into these three forms, it is uniform over the observers, variation of the human beings. That means every human being has similar responses, exactly similar, almost same, and same color chart is applicable for them, except if you have some diseases like color blindness. So, but this is very important because then we can consider developing technology, etc., based on this observation, and that is what we did. We acquire color into three components through optical camera, into red, green, blue components. Also, when we display color, we use this concept of either color mixing or color subtraction to produce sensation of all different kinds of colors. Use only three primary colors production, and then mixing or then appropriate mixing you can generate it. So three numbers are sufficient for encoding color. That is what is the summary, and it's quite old theory. It dates back to 18th century by Thomas Young, and more than 200 years old. So the laws of this color mixing, as I mentioned, that it is a kind of the same as we apply for analyzing a linear system. So it is a linearity which also is applied in this law. So it is a kind of linear, as I mentioned also. So which means that if we have two color signals, each has its own, say, primaries, components, representation, three color representations, and if we mix them, right? If you mix them, and if you add those, component wise, if you add them and if you mix them, it will generate the same sensation if you also mix those two colors, if you also superimpose those two colors. So that is the one part. The other part is that so mix two test lights, then mixing the matches will match the result. This is the second statement what I mentioned. The other statement is that same set of weights, then they match each other. So if there are two colors and they have the same components, then their sensation is same. So it is already we mentioned that. And the third thing is that if we scale the components, we have the same color experience, only the brightness varies. So it gets more brighter if you scale it further. So because of this linearity, we talk about linear color spaces, and that to 3 dimension, because you apply in 3 primary. So as if we consider a 3-dimensional vector space and a linear space, and every coordinates can be coordinates of that space represents some color. So the matching functions, so the weights required to match single wavelength light sources, as I just mentioned. This is what is matching function, which is the color chart I just mentioned. If you make a table and if I represent in the chart that suppose there are 3 primary colors, say C1, C2 and C3, then the component of a color. So if I say lambda naught, it is represented by certain amount, say x, y, z. Say so this is the matching functions. So this x, y, z are the weights or this color chart you can produce. So with varying wavelength you can produce this chart. And from the theory you can say that if I have just 2 light sources, by mixing them we can produce only a few colors, which can be also explained in terms of combinations. It's a point on the straight line formed by them, line segment, straight line segment formed by them. And but if you have 3 colors, then you have a much expanded zone, or much wider zone, where even the interior part, all the points in the interior part, they can be obtained through mixing of these 3 components. So it's a kind of plane coverage of plane. So we can see later on that actually when we represent a color, the chromatic information can be represented by this 2-dimensional form, where the 3rd dimension would be the intensity. We call it separations of color components into chromatic and achromatic form, which is not very clear in the RGB or red, green, blue component wise division. So we are coming to that part. So the first thing here we would try to understand that if I know the color matching function, so suppose I know the color matching functions, and which means I have these tables. I have C1, C2, C3, and then lambda naught, say lambda 1, 2, say lambda n. So there are different wavelengths, and I know the corresponding components. So this is available to me through standardization by creating this color table or color matching function. And if I consider any arbitrary color signal whose spectral, which means I know its spectral color distribution, right? So what should be the representation of this signal into this form? That means what are those components of this form? Because that will represent this color signal. So that is how we are going to compute it. So in this case, as we can understand that what we can consider, suppose you have this lambda 1, lambda naught, say this is lambda naught, say this is lambda 1, whatever. So this lambda naught will produce, say this is x1, x2, x3, and lambda 1, say y1, y2, y3, and and these are the relative coefficients. So this is A and say this is B. So it shows these relative coefficients or spectral amount of energy it has, not only relative amount of energy. So what we can do then in that case, at least for these 2 components, I know that it is AX1 plus AY1, then for AX1 plus BY1, because lambda 1 it is B, so AX1 plus BY1, AX2 plus BY2, AX3 plus BY3. So if my color signal contains only these two signals, lambda 1 and lambda 2, using this color table, I know that these are the three components which will represent my effective color. Now you extend it. So you consider all possible lambdas and you go on, computing them in this fashion as a linear combination of those components. Now this can be conveniently represented in the form of a matrix, and then what we can do, so this C is that color matching function, and you can see that this column is represented the response for lambda 1 wavelength, the response it gets into three primary channels, C1, C2, C3, and for each one. So if I want to multiply of the component of say T lambda 1, which means given T lambda 1, it will produce T lambda 1 into C1 lambda 1, T lambda 1 into C2 lambda 1, and T lambda 1 into C3 lambda 1, right? Similarly, if I say T lambda n, it will produce T lambda n into C1 lambda n, T lambda n into C2 lambda n, and T lambda n into C3 lambda n. So in this way, we just add them. So this can be conveniently represented by a matrix multiplication. There are three rows. So this E will be a 3-vector form. You can check with the maximum with the matrix dimension also. So this is how for any arbitrary color signal you can compute its representation with these three components. So let me talk about now different kinds of color spaces, and one of the color space where we directly acquire the signal is the RGB space, or red, green, blue space. As you have seen that three primary colors, here is the red, green, blue, three primary colors, and it's a three-dimensional space where you can consider any point in that space represents a color. But as I mentioned that in the visual system, we have also negative response. Now this shows the corresponding visual response. So this is for red response, this is for green response, and this is for blue response, which is shown here by C1, C2, C3 respectively. And you look at the shaded zone. So this shaded zone actually shows the range of wavelengths where the response is negative in our visual system, which means in the RGB space you require negative axis of red. So there are negative zone of color representation, and that's why you require also subtractive matching there. But the problem is that, as I mentioned, either you can make subtractive or additive mixing through our technology. So normally when we consider the space which are used for the purpose of color production in display devices like CRT, cathode ray tube, or LCD displays, there this mixing, and there the amount of these components, this red, blue and green, those are the primary, acting like a primary, and we can encode them into a vectorial form, say 100, which means other two are non-existent. So you can just normalize them into this range, and every color can be represented as a point, which are reproducible, of course, using this mixing this by these things. Another thing you can observe that the diagonal points, so if this is red and then this is cyan, so and if this is blue, its diagonal produces yellow. If this is magenta, if this is green, then its diagonal produces magenta. Actually, we consider them opponent color, because if I superimpose green and magenta, it would give me white. If I superimpose red and cyan, it would give me white. If I superimpose blue and yellow, also it will give me white color. So they are called complementary colors. So there is another space, that's why this complementary color space of RGB space, which is called CMY space or CMY model. Now, in this sense, now we better understand color in terms of red, green, blue, and also the color productions. Here, we usually in printing, the dyes are of this color: cyan, magenta, and yellow. Because now, if I print cyan, actually it absorbs the red quantity. So, amount of red quantity it absorbs, amount of green quantity it absorbs, amount of blue quantity it absorbs. That produces that set of colors. Again, as I mentioned, that all possible colors are not producible by these three primaries, either CMY or RGB. RGB has a range, CMY also has a range. Now, so there is a requirement of a representation of this color in such a way that this negative and positive factors maybe there is some kind of complexity in representation. So, can we consider a color space only which requires additive mixing for representing any color? Now, this is hypothetical. Physically, you cannot have those kind of primaries, but there are certain primers. So, mathematically you can have. Mathematically, we can make a linear transformation of RGB primaries to another three primaries, and so that the all such component mixings, so the components factors would be always positive, right. So, this one such space is XYZ space, and this space is proposed by Commission International Directorate, actually color body of international color representations, and CIE, we acronym we better attribute them, and they have a transformation. They have suggested this transformation. It's a linear transformation and invertible. So, from given red, green, blue components, you can convert into XYZ component, and given XYZ component, once again you can invert it back. So, this is a idea. So, you can see that there are some negative mixing of producing red. Say XYZ, there are some negative mixing. So, from XYZ component, it is not possible through additive mixing of red, green, blue. So, that is why it is a hypothetical color space, but it is represented better by this one. So, we have CIE XYZ, which is a linear color space, and here it is shown that in this color space, if I again plot those visual response of our spectral response of the respective filters, that means the filters for X, Y, Z, these three components filters. So, there actually we can see that every response lies in the positive zone. So, this is what is indicated here, that effective longer wavelength response has become also positive in those cases. And there is another way of understanding this part, is that you can better separate out the chromatic part and achromatic part. So, achromatic part is mostly representing the brightness. So, if I consider sum of X, Y, Z and take the average, actually that gives you a kind of a brightness factor. So, if I and the rest so if I know the sum X plus Y plus Z, then if I represent other two components simply by normalizing them, this is also sufficient to give me back once again the color representations, the full color informations of all the components. So, so my representation would be, say, X plus Y plus Z, X and Y, right. So, this X and Y are normalized. So, this can also give me back this one. Now, this part is representing the achromatic part. Actually, 1/3 of that will be the kind of approximately intensity values of the color, and X and Y, they bear the informations related to the chromatic part. So, it is a two-dimensional space. So, if I just restrict my observation on this two-dimensional point set, and as you understand that since these are all positive quantity, so they will vary mostly between 0 to 1. These values would be, their variation is between 0 to 1 because they are all fractions. and positive fractions. So now if I make a scattered plot of known colors whose components are known, then we can see that the shape of the scattered plot, it is a kind of half elliptical kind of shape, where inside this ellipse you have all the color points represented, and you can observe that also visually to make it more perceptible. We have also shown those color variations. So in the scatter plot, respective wavelengths, colors from the wavelengths are also shown. You can see this is the red zone, 700 nanometer, and in the periphery, if you move, the wavelengths gets smaller and smaller, and this is the blue zone, this is the green zone, right? And since now, if I consider the additive mixing, so if these are the three primary colors, then it forms a triangle, and all the points within this triangle, so all these points within this triangle, they form the possible colors which could be reproduced through additive mixing of this primary. So if you take any three primaries in this particular plot, we call it XY chromaticity chart. So if you take any 3 points, so whatever triangle you get in this point, so that triangle will provide you only those are the set of reproducible colors. So we call it actually gamut triangle basically. So this triangle determines in this particular color space. So this space is called CIE chromaticity space, and there are certain interesting property that we observe in this space, certain structure. One structure I have already mentioned. This is the variation of wavelengths across this structure. The other thing is that, as you know, that if all components becomes equal, which means if the values, there are 3 components. So mostly if I consider this zone, which is around say 0.33, so 1 by 3 and 1 by 3, near about that values. So it is 0.33. So that point is the achromatic point. That's the white point. So its color is white. And if you move towards periphery, it's basically the color, it is getting more and more, the color getting enriched, or I say the getting pure. So if I move radially, it is trying to attain it represents the color of a wavelength, the pure color of that wavelength. In between, it has certain some kind of whiteness. So the measurement, when we represent a color, there are 2 factors by which this color is represented, and here are also some examples that how different kinds of color of different kinds of light sources, they are represented through this chromaticity chart, because some light source has certain color, and you can see this is for the sunlight at noon, and 4870 K is the temperature for the black body radiator, and this is something like northwest skylight 25,000 K, which is a bluish tint. So those things are can be also observed through the scatter plot. One can analyze it. Now, just to give you a more some of other related information, a simplistic model by which you can represent a color informations and associate them with the representation by pure monochromatic lights color. So if I consider this is white point, and as you know, this periphery is representing periphery is associated with the variation of lambda. So if I move radially towards periphery, so you are hitting one of these lambda, which means if there is any reference direction, if I move angularly, I am varying the wavelength, and if I go radially, then I am varying the purity of the light. So more pure the light, we call it more saturated. So there are 2 factors for color representation. One is called saturation, and it is called hue. So hue is attributed to the no, the property by which the colors are, these electromagnetic wave sensations are distinct. That is the color sensation. And saturation is how pure is the color. So this is what I mean. Hue can be shown by simple model by some angle. So hue of that point, any point is that no, is if you draw a vector and if there is a reference point, suppose this angle can represent hue if you vary, and for this point this radius will provide you saturation. Actually the relative fraction of this radius over the maximum length that provides this saturation. So as I said, purity implies spectral color with maximum saturation. So with this now let me stop here today, and we will continue this discussion on color processing. Thank you very much for listening to my lecture.